So welcome back. In the previous video, we asked the question of whether there is some analog of a musical tone for light. And we said that the thing that really characterized these musical tones is having sound which is a combination of very specific frequencies. So in the case of a usual musical tone of a definite pitch, you have a fundamental frequency and then multiples of that fundamental frequency, and then not much sound at any other frequency. And that's very different from the typical spectrum of sound that you would have just from random noise. And so what we said was that for light, there's a similar phenomenon when you look at the light from hot gases of pure atoms, like this hot gas of hydrogen. If you look at the light from that and you figure out which wavelengths or which frequencies are there in that light, you find a very similar looking spectrum graph to the ones that we had for musical instruments. We have this light at very specific frequencies and then basically no light at other frequencies. And this is similar for hydrogen, helium, and other elements. And each one has some distinctive pattern. And so what we want to do is ask the question, what explains these spectra from the light from pure atoms? Okay, so why does the rainbow from a hydrogen light look like this with these very specific lines instead of the usual rainbow that you'd get from sunlight? Okay, so our starting point is going to be to remember why it is that the spectra of sound from a musical instrument has these very specific peaks. And remember, the reason was that in a musical instrument, the sound originates from standing waves. So these could be waves on a guitar string, or they could be sound waves in the tube of a wind instrument. But what we understood is that there are very specific patterns of oscillations that are allowed for these musical instruments. And each pattern of oscillation, this was something called a standing wave, each pattern of oscillation or standing wave has a very specific frequency. So we took that idea and we combined it with the superposition principle, which says that you could have multiple standing waves on top of one another. And this explained why when you pluck a guitar string, then you get a pattern of sound that might look something like this. So when you pluck a guitar string, then that oscillation you can think of as a combination of these standing waves, and each one has a specific frequency. That makes the air ultimately vibrate with that frequency. And so the sound waves that are produced are in this combination of frequencies. And so given that, and given that the atomic spectra look a lot like the spectra of musical instruments, you might ask, could there be a similar explanation for the fact that we get these specific combinations of frequencies or wavelengths in atomic spectra? So you could ask, is there something waving in an atom that would have a similar kind of pattern of standing waves? So let's think about the case of hydrogen. A hydrogen atom has an electron with a negative charge and a proton with a positive charge. And these are bound together by these electric forces that say that unlike charges attract each other. So there's kind of a classical picture of an atom that we might have where the electron would be orbiting the proton in a similar way that planets might orbit a star. And in this picture, there really doesn't seem to be anything that could be related to standing waves or really waves at all. There is an oscillation in this picture. The electron would be moving around in a periodic way, and that would have one particular frequency, but it's really hard to see where anything like a picture of standing waves could come in with this basic model. So turns out that this model is not really a good picture for how to think about the physics of atoms, to how to think about the physics of an electron and a proton in a hydrogen atom. This basic picture is really just incorrect. And in order to understand the correct picture, it turns out that you need the subject of quantum mechanics. Okay, so quantum mechanics is eventually going to tell us that this picture that we maybe started our discussions in the course with, where you wanted to understand the physics of objects and you assign them a position and a velocity, and then you just try to predict how those change with time, that's not really what you need to do when you're trying to describe physics at the atomic scale. So it turns out that in the correct picture, electrons and other particles are actually described as waves, just like our analogy between the sound and the light would suggest. And so I want to go over this basic picture of quantum mechanics. And our starting point for that, turns out, is the principle of superposition. So the most important thing in quantum mechanics is this principle. And so I want to remind you what this says for waves, and then I'll tell you how this leads to the basic statement in quantum mechanics. So what is the principle of superposition? It's something that says that if you are thinking about waves in a medium, then given any set of allowed waves, you can also consider the superposition of those waves, and that's also an allowed wave. Okay, so two waves can exist at the same time in the same medium, and the displacement is just the sum of the two displacements. So we had an example a long time ago where you had this wave, and then on top of it you had this wave, and then the combination wave, it looks like this. So those are all allowed configurations of the system. So that makes a lot of sense for waves. But what quantum mechanics says is that this principle of superposition actually applies to the configurations of any physical system. And that includes systems like a particle, like an electron in an atom. So the principle of superposition says that given any pair of allowed configurations, or any set of allowed configurations, you can also have the superposition of those configurations as another allowed configuration. So it's pretty hard to imagine what that means without talking about an explicit example. And so I want to just show you how this works in a really simple picture where my physical system is going to be this happy face that we used early in the course. So the happy face is basically just a representative of some physical object. It could be an electron, it could be a proton, it could be a whole molecule. Quantum mechanics applies to all of these systems. And so what I've drawn here on the top is one particular configuration that this physical system could be in. It has the object sitting at position 2 centimeters. Another configuration that our object could be in is the object could be sitting at position 4 centimeters. So what would we mean by a quantum superposition of those two configurations? So according to the principle of superposition, there should be a third configuration, which is a superposition of those two. One type of superposition would be where you have an equal superposition. So you have, in a sense, the first one and the second one in equal amounts, and we make this superposition. And I've tried to indicate that here. So what on earth does this mean? Well, this is supposed to be an allowed state of our system. And the way that we interpret this in quantum mechanics is to say that in this third configuration, our object does not have a definite position. We could still go in and measure the location of the object. And if we do go in and measure or observe it by interacting with it in some way, what we'll find is that either the object ends up at position 2 centimeters or position 4 centimeters. So when we actually go and observe it, we get something which is like an expected result. The object will be at a definite location. But the subject of quantum mechanics tells us that before we actually make this measurement, it does not have a definite location at all. Okay, and this is something that you can actually show using certain experiments. Just to give you a little bit more understanding of this idea of superpositions, I want to give you a couple more examples of allowed configurations of a single happy face. So in the previous superposition, we had an equal superposition of those two states. In the top picture here, I've illustrated an unequal superposition of these two states. So this is a physical state. It's kind of like adding two waves up where one has a bigger amplitude and the other one has a smaller amplitude. So in this configuration, again, if we were to make a measurement of the location of our happy face, we would either find it at position 2 centimeters or at position 4 centimeters. But in this case, we would have a 70% chance of finding it at the 2 centimeter location and a 30% chance of finding it at the other location. Now, that superposition involved only two possible locations, but according to the general principle of superposition, we can add up configurations with many different locations, and that sum should still be an allowed state of our system. So the more general configuration of the happy face that I've drawn at the bottom is such that if we were to make a measurement of its position, we might find it at 3 centimeters. That's the most likely outcome. But we might also find it at 3.5 or 4 or 5 or 6 or 0.5. All of these are possibilities, and each one has a certain probability. In order to describe these kinds of general superpositions in quantum mechanics, we use a mathematical object that's called a wave function. You've probably heard of as being associated with quantum physics. So the wave function basically just shows us how much of each configuration is in the superposition. And so this particular configuration, this particular superposition that I've drawn in the top picture, I've tried to represent that by a wave function in the bottom picture, which shows the largest value where we're most likely to find the object, and smaller values where we're less likely to find the object. Okay. So that's the idea of a wave function. And general wave functions, so in order to specify a general superposition or the general configuration that an object can be in, you just have to consider these general wave functions. So this wave function replaces the idea of specifying a position and a velocity for an object. And we need something that then replaces Newton's laws. So remember, Newton's laws allowed us to predict future positions and velocities from the current position and velocity. So now in quantum physics, we need something that will allow us to predict the future wave function from the current wave function. And that's the thing that we call the Schrödinger equation. So the Schrödinger equation tells us how this superposition will change with time. Or equivalently, it tells us how a wave function will change with time. And if you investigate the physics of the Schrödinger equation and see what it predicts for how these wave functions change with time, it turns out that that is very, very similar to the way that sound waves and other waves change with time. So this is one of the reasons we call it a wave function, because the physics of these wave functions is very, very similar to the physics of waves that come up in other contexts. So let's finally return to our system of the hydrogen atom. And so now instead of the happy face, we're going to think about the electron. And So in the hydrogen atom, remember the electron being negatively charged is attracted to the proton. And so we could think that there's some region around the proton where the electron is confined to be, but it could exist at many different possible locations within that region. Now in quantum mechanics, the general state of the electron in the atom is going to be described by one of these superpositions, or equivalently by a wave function, and that wave function will evolve with time by the Schrdinger equation. And it turns out that just like waves on a guitar string, this wave function that is describing our electron in the atom, it has certain standing wave patterns. And these standing wave patterns have very particular frequencies. And so, in a sense, the physics of the electron in the hydrogen atom is very, very much analogous to the physics of a guitar string or the physics of air inside a wind instrument, in the tube of a wind instrument. In chemistry, these particular standing wave patterns for electrons are called orbitals, so you've probably heard that before if you've taken chemistry recently. Now, there is a slight difference between the connection between these standing waves and the spectra in sound versus with atoms and light. So with a guitar, the various standing wave patterns, those ways that the string could vibrate, they directly led to vibrations of the air that had the same frequency and led to sound waves with that frequency. With atoms, the particular standing wave patterns in an atom for an electron, they don't directly cause the light that a hot gas would be producing. It turns out that the light is actually coming from what we call transitions between these standing wave patterns. So the electron could be vibrating in this one standing wave pattern and then make a transition to a different pattern of vibration. And when it does that, usually some energy is released because the patterns with a higher frequency, they also correspond to configurations that have a higher energy. So when the electron goes from one standing wave pattern to the other standing wave pattern, then some energy is released, and that energy it takes the form of light with a specific frequency. Okay, so that one extra element then explains why we get this kind of a spectrum coming from a hot gas of hydrogen. Okay, so let me review then. When you have an electron in a hydrogen atom, its wave has specific standing wave patterns. And the general motion of an electron would be a combination of those patterns. The patterns each have a specific frequency associated with them. And when the electron makes a transition from one pattern of vibration to another pattern of vibration, at that point, energy is released, and that takes the form of light with a specific wavelength or frequency related to the difference in frequencies between the electron standing wave patterns. So this line in the spectrum of hydrogen comes from a transition between the number 3 pattern in my chart to the number 2 pattern. This line comes from a transition between the number 4 pattern to the number 2 pattern, and so forth. And you might notice, well, there are a lot of possible transitions missing here. Why don't we have all of those ones in the spectrum? And the answer is that we actually do. So this spectrum that I've shown is only the spectrum of electromagnetic radiation within the visible part. There are other parts of the spectrum coming from transitions 2 to 1, 3 to 1, 4 to 1, but those correspond to light in the ultraviolet range. Okay. So this pattern of standing waves in for the electron in the hydrogen atom actually kind of perfectly explains the spectrum that we observe in hydrogen. Okay, and similarly, if you look at the more complicated elements, they have more electrons, but those combinations of electrons also have standing wave patterns. Those also have specific frequencies, and the spectra from those more complicated atoms can also be understood through the transitions between standing wave patterns with different frequencies. So I want to finish just by kind of summarizing and telling you that this theory of quantum mechanics, which is really fundamentally just coming from the principle of superposition being applied to general physical systems, this is believed to be the most fundamental rule. These things are the most fundamental rules that we think govern the physics of our universe. It applies to all elementary particles and really any physical system. And so what's kind of amazing is that the physics and mathematics of quantum mechanics is actually almost the same, as I've tried to emphasize in this lecture, almost the same as the physics and mathematics that we use to understand music. So this is really fascinating because for really thousands of years, actually, starting from the ancient Greeks, physicists and philosophers believed that music was somehow intimately connected with the workings of the universe. And they worked in all sorts of ways to try to understand this connection. And so what strikes me as truly amazing is that in a sense, all of these people were right. There is this deep connection between the physics of music and the most fundamental physics of our universe, which is the theory of quantum mechanics.